everyone. People are actually awake at this conference in the morning. It's weird. So, my first tech conference was Golden Gate RubyConf 2010, and Jim Weirich gave the keynote at that conference, and he covered a wide variety of topics, including physical chemistry, which really is one of my favoriteest things in the world, emission spectra, and this book, The Structure and Interpretation of Computer Programs. He said that this book had been recommended more than any other book to him as something that would help current programmers, professional programmers, improve their craft. And so he had started a study group, and his keynote was about what his study group had learned thus far in the first 2 chapters of this book. So this book has 5 chapters. It's about this thick, so you can imagine what those 2 chapters actually cover. And about 50, 60 minutes into a 90-minute keynote, he said, and everything I've covered thus far doesn't use assignment. In fact, this book doesn't even introduce assignment until chapter 3, more than 40% of the way through the book. And that little nugget stuck with me, and that's kind of where this talk started. So, a little bit about me. I'm Aja Hammerly. I tweet at ThagamiserRB, and I like it when people tweet at me during my talk because my phone's over there, and I will read all your comments later, and I will be very happy, as long as they're nice. I'm on GitHub as Thagamiser. I blog very occasionally at thagamiser.com. Primarily, it's my talk slides. And these slides would be up there, except for me and rsync had an argument about an hour ago. And I work at a company called Substantial. We are a digital product studio in Seattle, Washington. If you're ever in Seattle, you should check out our website, substantial.com, because we host far too many events in our office space for nerds of varying kinds. What qualifies me to give this talk? Quite frankly, not much, but based on Jim's keynote, a couple of us in Seattle RB did a study group through SICP. Took us about 9 months. Ryan's going to talk to you a little bit about that later. And I also did a study group on functional programming last fall in a different book. And if you've ever seen me speak before, I have a deep fascination with esoteric and not very useful programming languages, like Prolog and other such things. So once I've started doing that, I'm starting to see some functional programming all over the place now. So, functional programming. What's that? This is what Wikipedia has to say about functional programming. In computer science, functional programming is a programming paradigm, a style of building the structure and elements of computer programs that treats computation as the evaluation of mathematical functions and avoids state and mutable data. So that is not particularly useful. This is what one of my coworkers said. The entire idea of mutable state is suspicious and easy to mess up. And this was Jim's definition from his talk. A functional language is about calling functions. No, it's not about calling functions, it's about creating functions that do things. So I don't actually think I could build a talk around any of those definitions. So in this talk, I'm going to focus on one core aspect of functional programming, and that is not using assignment. No assignment at all in this talk. There's not a single equals in Ruby anywhere in this talk. In Scheme, you do assignment with setbang, and there are no setbangs in this talk. And I'm going to avoid modifying objects anywhere. So, setting expectations, 114 slides. Lots of code. I don't give fluffy talks. Lots of parentheses. Yeah, lots of parentheses. And no ponies. Sorry, Mike. Yes, but it's a very sad pony. So, why should you care? Not why should you care about no ponies, but why should you care about functional programming? So, first of all, it's easier to test. There's a lot less setup. There's a lot less stubbing and mocking. In fact, most of the times in the projects I'm working on that have functional aspects, there's very little stubbing and mocking. And you always start from a known state, which means it's impossible for your tests in your first run to pollute the data for your second run or your third run. You don't end up with those dependencies that can trip you up pretty easily. Concurrency is a lot easier in with functional paradigms because, again, no state. Nothing for 2 threads to stomp all over each other on. It's fantastic. Safe reuse. This is something that a lot of functional programming advocates talk about. You can take a function from one project, pick it up, move it wholesale into another, because, again, you don't have state. You don't have to make sure you have class vars and instance vars set up correctly for your function to work. Brevity. This is a plus or a minus, depending on your opinion. A lot of functional languages, Lisp languages, Scheme, Haskell, are concise. They're very short and very concise, and not a lot of text goes into making something happen. That makes some people very happy. It makes others frustrated. Your mileage may vary. But I think two of the biggest reasons that you should care about functional programming is that a lot of you already use it. Who here has passed a block to some method from enumerable? Raise your hands. That's what I expected. That whole idea, functional programming, or at least strongly influenced by functional programming. And since most of you are already doing it, you might as well learn the basics of it and start doing it right and really using all the strength it has. Also, Ruby makes it easy. A lot of the basic functional concepts are available to us natively in Ruby. You don't have to go through any crazy contortions to make them work, and so it makes it easy to integrate a little bit of functional stuff over here. Maybe you've got some service in your Rails app that could benefit from some functional ideas. You can build that up, throw it in lib, and you can leave the rest of your Rails app in object-oriented land. So, this functional language I know best that actually has use in the real world is Scheme. So here are some Scheme basics. This is going to be a very fast trip through Scheme 101. Most important thing, Scheme uses prefix notation, which means that the method goes first. So throughout all of my slides where I have Scheme and Ruby on the same slide, Ruby is in red and on the right. R's, alliteration, they're awesome. Scheme is going to be in blue and on the left. So you can see that 5 plus 3 in Ruby is the same as plus 5, 3 in Scheme. And the cool thing about prefix notation is that you can have as many arguments as you want. So you can add 2 things, or on the second line, you were multiplying 3 things. It's the same method. You can do your parentheses for grouping of various mathematical functions. You can see that in the third line, and then there's the add 1 function, which I think actually is in Racket Core, a simple incrementer. And you put the function name first, and then you put the arguments afterwards, surround everything with parentheses. Lots of parentheses. Here's how you define functions in Scheme. One of the things I really like is that it looks a lot like Ruby. We've got define, a function name, some arguments, a method body, and then a closed parentheses instead of an end. And then you call the method just by having the method name and then the argument inside parentheses. It goes really nicely one-to-one with Ruby. And then conditionals. One thing that I see that functional programmers, especially schemers and racketeers, use a lot is the cond. The cond is short for condition, and it maps one-to-one with Ruby's case statement, which I see people almost never using. So here's how it looks. And this function is absolute value. So first case, if our number is greater than 0, we're going to say our number is x. If it's greater than 0, we just return the number itself. Second case, if the number is equal to 0, and that's single equals in Scheme is a comparison. It's like the double equals in Ruby. It is not assignment. I am not breaking my rule. We return 0, so if our number is equal to 0. And in the other case, we return the mathematical opposite. So -1 times the number in Ruby, or Scheme has a unary minus that works as the mathematical opposite, and it's awesome. We return the net mathematical opposite. And just like Ruby, it has that implicit return. Whatever the last statement you evaluated will be returned. So you can see how that maps one-to-one. But this is not actually how a schemer would write it. That's how a real schemer would write it. And this is where that brevity point comes in. It shrunk a lot vertically. I've been trying to lay stuff out in the last slide so that you can see side to side how it maps with the Ruby, but schemers like their code short. So the other kind of conditional that I'm going to use in this talk, although it's used a lot less often in a lot of the Scheme code that I've read, is if. So here's a predicate function. Who here does not know what the word predicate means? Raise your hand. Awesome, thank you. Predicate functions are functions that return a Boolean, so they either return true or false. And that concept's really important, and I'm going to use it all over the place. So this function returns balmy based on the temperature. Is it balmy outside today? So if the temperature is above 65 degrees, it's balmy. If the temperature is not above 65 degrees, it's not balmy. Some of us are not you. So temperature, so you can see in Scheme we have an if, we have a conditional statement, and then we have 2 branches. One that gets run when our condition is true, and one that gets run when our condition is false. The else is implicit, unlike Ruby. You just have 2 branches. So that's how an if works in Scheme. And finally, lists. All the functional languages I've ever used love lists. They use them all over the place. We don't really have a concept in Ruby that maps one-to-one with the concept of a list in Scheme, so I'm going to use arrays and just kind of hand wave over the differences. So in Scheme, you define a list with a single quote, a set of parens, and some elements inside separated by spaces. In Ruby, there's an array 1, 2, 3. That's a list. I don't know the meaning behind the word car. I don't know the origins of the word car, but in Scheme and Lisp, car is the first element of a list. It's the head. So, thank you. See, I learn things when I give talks. It's awesome. So the car of the list 1, 2, 3 is 1. And in Ruby, our equivalent is first, also 1. All functional languages I've used have a concept of rest. In Scheme, that's cdr. And in Ruby, we define it with this crazy array index range syntax of 1 ... -1. That's ugly and hard to write. So I'm going to open up the array class and add .rest onto the end, and that returns the exact same thing. So rest in this case is a list that is the rest of the elements, not including the head. In this case, that's 2 and 3. So the list containing the elements 2, 3. And finally, you need to know if lists are empty. In Scheme, that's null ? And in Ruby, that's .empty-a. And one thing I did not point out on the conditional slide is that Scheme uses £t for true and £f for false. If that really bugs you and you want to learn a functional language, you can go to Racket. It has true and false built in. So now we have all that. Now for my favorite thing, recursion. Awesome. Factorial. This is the definition of factorial in Scheme and Ruby. If our number we're trying to find the factorial of is 1, we return 1. Otherwise, we take n times the factorial of our number minus 1. So if we're going to try to find the factorial of 5, we'll take 5 times the factorial of 4, times the factorial of 3, times the factorial of 2, and then you get down there, because recursion is awesome. There was a great lightning talk last night about Fibonacci and elegance and how Ruby is awesome. I promised to show a Scheme implementation of Fibonacci. Here it is. So this gives you the nth Fibonacci number. If n is 0, we're going to say that that Fibonacci number is 0. If n is 1, we're going to say 1. Yes, I know that there are differing definitions of the first two Fibonacci numbers. This is the one I like. Otherwise, we're going to take the Fibonacci of n minus 1 and the Fibonacci number for n minus 2 and add them together. It's the definition of Fibonacci. And you can see, again, side by side with Ruby, how that works out. And these are all fantastic, but there's this thing called tail call optimization that makes these things even more awesome. So, another recursive example. Exponentiation. This is a function that computes b to the n. And if n is 0, any number raised to the 0th power is 1. We return 1. Otherwise, we multiply b times b to the n minus 1. Again, recursion is awesome. Except there's a small problem with this. Stack depth. Stack depth gets pretty high with this version. So, walking through, if we start with x of 2 to the 4th, well, we're going to go 2 times x of 2 to the 3, all the way down to 2 times 2 times 2 times x to the 2 to the 0. And then we're going to unwind the stack, and I've color-coded each level of the stack as it unwinds, and we end up with a stack depth of 5. And 5 is not that big a deal, but if you start computing really big powers, you might run into some problems. So the way you can fix that is by using tail call optimization. My title on this slide is wrong, I apologize. And so what we're going to do instead is we're going to use an accumulator, and we're going to write a helper function. So we still have our x of b to the n, but now we have xt with b to the n and a third argument. And that third argument is our product so far, our partial product, which is why it's p in our helper function. And what we're going to say is that our n is now a counter, and we're just going to tick it down by 1, and we're going to increase our product by one factor of b. And that means that we're going to have less work to do when we unwind our recursive stack. So if our counter is 0, we're just going to return our product, because if our counter gets down to 0, we're done. Otherwise, we're going to call our helper function with b. We're going to reduce our counter by 1, that's c minus 1 line, and we're going to go b times our partial product thus far. And it's a little hard to follow, so here's what it looks like as you actually move through it. We start with x of 2 to the 4, and then we do our helper function with 2, 4, and a partial product of 1, because 1's the multiplicative identity. And then we call ourselves again with 2, 3, and now we've multiplied our base times our identity, so that's 2 as our partial product, as that last argument. And then we go we reduce our counter and increase our partial product again. So we have 2, 2, and 4, 2, 1, and 8, 2, 0, and 16, and there's our answer. Our counter is now 0, so we can return that partial product as our final answer. So we still end up making 5 recursive calls, but since at every point in the process we've done all of our math, we don't have nearly as much work to do when we unwind the stack, and it ends up being a lot more efficient. So the meat of the talk, as always when I give a talk on a crazy programming paradigm, is a semi-contrived example. This case is the making change example, which I have found in every functional programming book I have worked on except one. And I've probably implemented it in 4 languages at this point. So the problem, as stated in SICP, is how many different ways can you make change of $1 given half dollars, quarters, dimes, and nickels? So I'm going to walk you through my thought process as I sat at home one afternoon writing this example up for this talk. And my first response was, that's too hard, so we're going to simplify it. How many ways can you make some amount with some coins? Well, at that point, I know kind of what my function signature is going to look like. I'm going to define a method, countChange, and I'm going to give it an amount, and I'm going to give it some coins. You know, that's kind of where I ended up. So let's say an amount is an integer number of cents. If you've ever worked in billing systems, this idea of an integer number of cents is probably familiar to you. And I'm going to assume I have infinite coins, which would be awesome. So I'm going to make my coins collection an array of denominations. So a penny will be represented by a 1 in this array. A nickel will be represented by a 5, and so on. So back to our simplified original question. How many ways can you make some amount with some coins? Still too hard. We're going to simplify again. How many ways can you make 1 cent with no coins? Anybody got the answer? Yep. Easy answer. See, I like making things simpler. It's awesome. So let's write some code for that case. So let's add a case statement, because functional programming, case statements are awesome. So when our coins array is empty, we have no denominations, we have no coins, we can't make change, so the answer is always going to be 0. Yay for a base case for our recursion. We test it out. We say, how many ways can we make 1 cent with no coins? Empty array to represent not having coins, 0, so it works. And because I know I'm going to be doing recursion, and I know I have very limited side-to-side room on my slides, I'm going to alias countChange to CC. Run it again, still works. So how many ways can you make 1 cent with pennies? Yep, penny. So I'm going to fade out the code we've already talked about, just so you can focus on the part that's important. So we had another case. If our amount is equal to our first denomination, we have one way to make that amount, right? We just use one of those first denominations. So run it, totally works. Awesome. How many ways can you make 5 cents using pennies? 1. That many pennies right there. Is this reminding anyone else of their 3rd grade homework? So another case. This is going to be our else. And we're going to have to start using recursion now. So if we don't know what else to do, let's grab one of those first coins in our denominations array. Let's say, OK, I'll use 1 penny. Now, code, go figure out how to make 4 cents using whatever coins I have left. And then it's going to go, OK, well, I'll use 1 penny. And now, code, go figure out how to make 3 cents using the coins I have left. And eventually, we're going to get down to one of our base cases, and we're going to be done. So simple recursion. Test it out. 5 cents, pennies, totally works. Make it even more complicated. How many ways can you make 5 cents using nickels and pennies? Yep. So let's try it, see if we got it. Doesn't look right. Doesn't look right at all. So, at least for me, it wasn't obvious what was going on when I was coding through this. So I looked at my code and I'm like, this doesn't make sense. So one of the things I like to do is I like to substitute in my arguments. So I've bolded the args. And now I'm going to step through each case and figure out where I'm going wrong. So the first case doesn't match, so that can't be the problem. Second case matches, though. And what's happening here is we're saying, well, I'm making 5 cents. I have nickels. Clearly, I can make 5 cents with a nickel, and so I'm done. Except we know that you can make 5 cents using nickels or pennies. So I think we're missing a recursive step here. And what we need to do is we need to say, okay, it's fantastic code that you can make 5 cents using nickels. Now can you use the rest of the coins that you have and see if you can make 5 cents using those? So here's where that .rest we talked about earlier comes in. We're going to say it's 1, so we can use that nickel, plus however many ways we can make 5 cents using the rest of the coins. Recursion, it's awesome. So let's test it out. Count change of 5 cents with nickels and pennies, we get 2. So that's right. Let's make it even harder. How many ways can you make 10 cents using nickels and pennies? That look about right to everyone? 3 different groupings there. 2 nickels, nickel and 5 pennies and 10 pennies. So let's see if we have all the cases we need. Run the code, gives us 2. Still not quite right. So again, we substitute in the arguments. Again, we don't use the first array, first case. Second case doesn't match. So I think we're missing a recursion on our third step now. And it's exactly the same one we were missing before. Is our existing one is like, okay, well, that 10 minus 5 is saying we are going to use a nickel. But we know that we don't have to use that nickel. So what we need to do is we need to add a second case where we're going to be like, okay, well, how many ways can you make it without nickels? And how many ways can you make it with nickels? And this is an idea that I learned in school called weirdo analysis, where you say that one thing that you're trying to count is the weirdo, and you count all the ways you can do it with the weirdo, and all the ways that you can do it without the weirdo, and you add them together. So in this case, our nickel is the weirdo. So we're going to count all the ways we can make 10 cents without a nickel, and all the ways that we can make 10 cents with a nickel, and we're going to add them together. And I Googled it, and other people call it weirdo analysis too, so while I may be a weirdo, I'm not a weirdo because of this. So we're going to count change, 10 cents with nickels and pennies, we get 3. So this is where my tester brain kicks in, because I used to be a software tester, and I'm like, how many ways can I break this? How many ways can you make 7 cents using only nickels? Yep, there aren't any ways. So I run my code, stack depth too deep. So I think we're missing one last case. This is just not good. So substitute the arguments in, and at this point, here's the place where it's going wrong. All the other stuff's fine. We get to this case where we're like, okay, well, we'll use a nickel, and we'll go 7 cents minus 5 cents is 2 cents. We'll say, hey, code, can you make 2 cents using nickels? And the code will just keep going, nope, nope. So how many ways can I make negative 3 cents using nickels? How many ways can I make negative 8 cents using nickels? So we're missing one last case, and it's this case. If our amount is less than our biggest denomination, we need to try to make our amount using the rest of our coins. And at this point, I've introduced very subtly a requirement, and that requirement is that the coins array is in descending order by denomination. Otherwise, this won't work. So I don't think that's a bad assumption to make, but I did make that assumption, and I wanted to make that clear. So we run it, we get 0, that's correct. And at this point, we're able to go back to our original problem, which is how many ways can you make change of $1 given half dollars, quarters, dimes, nickels, and pennies? There's the code. Answer is 292. And here's the implementation in Scheme, which I still think is much prettier than the Ruby implementation. But it's a RubyConf, so I did it in Ruby. So it's exactly the same as the Ruby version. We still have the same 4 case statements, or 4 whens on our case statement. So brief side, we're going to do some more functions. Who here knows how to use include in Ruby? Hands. Good. OK. It's called member in every other language known under the sun, pretty much. So is this thing part of this list? That's all it does. Here's a recursive definition. If the list is empty, clearly our thing can't be in it. If the first thing of our list is the thing we're looking for, well, clearly our thing is in the list. Otherwise, go see if our thing is in the rest of the list. Basically, the exact same logic we were just using for counting change. Here's the same function in a slightly smaller font, because here's exactly the same logic used to implement any A, the any predicate on enumerable. The only changes I've made in this case is instead of passing in an element that I'm looking for, an n, I'm passing in a predicate function. And we're going to call that predicate function on the first element of the list, and if that returns true, we're going to return true. Otherwise, we're going to recursively call exactly the same way we did with member, and pass the predicate in instead of the element. And this is what I say, that this idea is built into Ruby, fundamentally. These concepts, the fact that you can pass a function as data in Ruby, really makes it powerful for doing functional ideas. And you can look at how simple that transformation was. So here's the actual implementation, and to use this, I like to use anonymous functions. If you're a JavaScripter or a CoffeeScripter, you probably use these all the time. If you're a Rubyist, you probably use them less often. But you can see side by side the Lambda implementation of an anonymous function in Scheme and the Lambda implementation of an anonymous function in Ruby. They're really similar. Ruby really was influenced by Lisp, really was. And you can see that in the case of Ruby, you do .call in the end, call it. In the case of Scheme, you call it the same way we call any other function. Add a parentheses, put the arguments on the end, close parentheses. So we can use those anonymous functions with our any predicate that we just built up. And we're going to say any for the list of 1, 2, and we have an anonymous function that checks to see if anything in that list is less than 5. And the answer is true. And then we run it again with an anonymous function to see if anything in that list is equal to 5, and the answer is false. But this idea of passing functions as data is built into Ruby and is really powerful. So I have very little time left. I highly recommend that you learn more. I've been talking about this talk as a functional programming one-on-one. This is really the first half an hour of functional programming one-on-one, and there's a lot more that you can learn, and I think that Rubyists especially can benefit from learning these concepts and using them within our language. And if you do JavaScript, you really should learn this, because JavaScript, especially a lot of well-written JavaScript, has a lot of these ideas in it too. My favorite functional programming book is The Little Schemer. It's really thin. I didn't bring it because I didn't have room in my bag. You could finish it in a weekend. I don't recommend you do, because it's dense. And it's written in Socratic dialogue. It's so awesome. It's 2 columns, questions on the left, answers on the right, all the way through. It's weird. There are 2 other books in the series, The Seasoned Schemer and The Reasoned Schemer. Once you get past The Little Schemer, I recommend those 2 as well. I have them all lined up on my shelf at home. The Reasoned Schemer builds a constraint-solving system a la Prologue by the end. So you can go from nothing to The Reasoned Schemer in probably less than 150 pages. And that shows you how dense these books are. And then structure and interpretation of computer programs. This was an introductory text on functional programming, or to programming completely, at MIT for a number of years. It's also known as the Wizard Book. If you do it, I recommend a study group. And if you do a study group, I recommend not doing what Aaron, Ryan, and I did. You don't have to do all the problems. We did them all. It took us 9 months. I don't recommend that. But this goes from reverse a list to implement a scheme interpreter in language of your choice. Like, that is the last problem in the book. So it also builds a constraint-solving system and deals with environments and all sorts of other awesome things. I did build a scheme interpreter in Ruby. If you want to see it, come find me later. As I said last night, I wear pink at conferences, so I'm easy to find. And if you're like me and you're more of an auditory learner, there are a lot of great talks on functional programming on Confreaks. Here are 4 of my favorites. Functional Programming in Ruby by Pat Shaughnessy from GoRuCo, 2013. Parenthetically Speaking by Jim Weirich. That's the Golden Gate RubyConf 2010 keynote that I watched and kind of got me down this path and was the inspiration for this talk. Sadly, the Confreaks video cuts out 45 minutes into a 90-minute talk, so most of what you get is physical chemistry and emission spectra, which I still think is awesome, but it's not quite as awesome. Also, there's Functional Principles for OO Development by Jessica Kerr from Ruby Midwest 2013. This is an awesome talk because Jessica's a great speaker, but also because she does functional programming every day, unlike me, and unlike a lot of people who give these talks. And so she has a very different interpretation of it. She's coming at it from a functional person who's interested in Ruby. And she's a very animated speaker, so you cannot fall asleep during her talks. And why not? Adventures in Functional Programming by Jim Weirich. This is the talk that was making the rounds of Twitter right after Jim died earlier this year, and it's a fantastic talk. I highly recommend watching the video. I was in the audience for this talk, and I understood the Y Combinator when I walked in, and I could barely keep up, because it is information dense. But Jim is a fantastic speaker, was a fantastic speaker, and so you should really sit down and watch this with your finger on the pause button to figure out what the heck he just did. Photo credits. If you're going to use photos in your talks, I highly recommend you credit them. I only had one this time, which was the boring board pony. Thank you very much. I have 30 seconds, so I have time for one question. Yes?
What's your
The question was, what's my opinion on Clojure? I haven't used it, but everyone I know who uses it is smart, so it's probably pretty awesome. Okay, thank you guys.